Okay, tell me, have you solved this question quickly? What is the answer? 4.69 you are getting. Okay, the first one is correct. It is 4.69. Okay, and how do we do that? You see, the number of uh, suppose if I write down here, the reaction is CH3COOH plus NaOH gives you CH3COONA plus H2O, right? So zero point 0.1 into 100, so we have actually here 10 millimoles of NaOH. 10 millimoles of NaOH. And for CH3COOH, we have 20 millimoles. So 10 millimoles react with 10 millimoles of this, right? And gives what? 10 millimoles of CH3COOH. So this is what? This is the limiting reagent in this reaction, NaOH. Right? When 10 millimoles of this react, okay, yeah, 4.69 is correct. When 10 millimoles reacts, so 10 millimoles of CH3CONA forms. Now, in the reaction vessel, you see, we have CH3COOH present, and number of moles of CH3COOH left is what? Number of millimoles left, that is 10 millimoles, because 10 reacts with 10, so 20 minus 10, 10 is left, right? And 10 millimoles of this is formed, right? So whenever you have mixture of the CH3COOH and CH3CONA present, then the solution is what? Solution is an acidic buffer solution. Acidic buffer. This gives you the pH will be equals to pKa plus log of concentration of salt by concentration of acid. pKa value from this you can calculate, that will be 5 minus log 2, which is around 4.7 or 69 you can say, right? pKa is equals to, like, pH will write minus log of Ka is the formula. pKa is equals to minus log of Ka. That formula we can using here. So it is 4.7 plus log of 10 by 10 is equals to 1, which is 0. So answer will be 4.7. Okay, so this is the first case. Now this is easy, it is a direct formula based question. Now the second case, you see, when we have added 50 ml of 0.1 molar HCl. Second question, you see, 50 ml and zero point 0.1 molar. How many millimoles? Millimoles of HCl. That will be 50 into zero point 0.1, that is 5 millimoles of this. Okay, so this is the acid that you are adding, right? So since the solution is a buffer solution, and in that you are adding this acid, so that will try to minimize the change in pH, right? So what happens when you add this HCl into this, the salt you have, that is CH3COONA, right? It dissociates like CH3COO minus and Na plus, right? And the acid that you have, that is CH3COOH, it gives you CH3COO minus plus H plus. Okay, so what happens in this? Now you see how this buffer solution works. When you add, this is the ion we have, because this is the salt of this, the solution of this only we have, buffer solution, salt and weak acid and this salt, right? All these ions are present, right? So when you add HCl into this, which gives H plus, so this H plus combines with this CH3CO minus. This H plus is coming from HCl, the HCl that you are adding. It combines from to this CH3CO minus, and this reaction goes backward and forms weakly dissociated or weakly ionized CH3COOH. And that is how it maintains the pH. Because you see, you try to understand here. You try to understand. We are adding HCl. We are giving H plus actually. If this H plus will not neutralize, then the pH of the solution will change. But the nature of buffer solution is what? It minimizes the change in pH. And how it minimizes? The extra H plus that you are getting from this acid, that has to neutralize. And that is neutralized by this reaction too. The H plus combines with the CH3CO minus and converts into weakly ionized or feebly ionized CH3COOH. And that is how the pH of the solution is maintained. The whatever H plus is coming from acid, that combines with this. Now what happens with this? First of all, 5 millimoles of H plus we have, right? 5 millimoles of this gives 5 millimoles of H plus, same millimoles. Now 5 millimoles of this combines with 5 millimoles of CH3CO minus, right? So in the reaction, the concentration of salt, that is CH3COO minus, decreases. This is salt. Why? Because we assume that this ion combines with H plus and forms CH3COOH, right? And the concentration of acid, which is CH3COOH, it increases because this reaction goes in backward direction, forms CH3COOH. Number of millimoles of CH3COOH was 10 initially, and for this also it is 10. Right, so this gives you 10 moles of this and 10 millimoles of this. Now, 5 millimoles of H plus combines with this, forms 5 millimoles, excuse me, 5 millimoles of CH3COOH. So number of millimoles of CH3COH will be what when you add HCl? 10 was initially present and 5 forms by this reaction with HCl. This gives you 50 millimoles of CH3COH. 15 COH millimoles of CH3COH. Now, the concentration of the salt will decrease. So initially it was 10 and 5 reacts, so it gives 5 millimoles of this. Is it clear? Tell me, is it clear? We'll calculate what is the answer. Is it clear or not? You tell me. So the point is what, when you add HCl, see, actually one question that you can ask me over here that I was expecting. But anyways, you see here, when I said the salt concentration is decreasing, why not acid concentration is decreasing? Why not? Why this reaction is going backward? Why not this reaction is going backward? See what I said, H plus that you are coming here. This H plus may react with this also and goes this reaction backward, no? See, the first reaction won't go backward because this is a salt, right? It is weak, it will be ionized easily. It exists in the forms of this ion only because this is not the stable form. In the solution, it exists as this only. But CH3COH is what? It is weakly ionized, right? And this is what, this has common ion effect also in these two equilibrium, correct? So because of common ion effect, CH3CONA will suppress the dissociation of this. So what we assume in this mixture, this anion is mainly because of the dissociation of this salt, not because of this acid, right? What we say that this acid is weakly ionized, so concentration of CH3CO minus in the solution is mainly because of dissociation of salt, not because of acid. So when this H plus combines, then we say, okay, mainly because of this salt only, when this H plus combines, then the salt concentration will decrease because it combines with H plus and converts into weakly ionized CH3COOH. And that's why we are saying that salt concentration will decrease and acid concentration will increase. Salt concentration will decrease and acid concentration will increase, right? Now you see, this is the concentration of salt we have and this is the concentration of acid when we add these many moles of HCl into it. Now we can use the formula of pH, which is again pH is equals to pKa plus log of concentration of salt divided by concentration of acid. That gives you pKa is 4.7 plus log of salt by acid is log of 5 by 15, which is 1 by 3. So 4.7 minus log 3, this gives you the pH of the solution. When you solve this, you'll get pH of the solution. So log 0.3 is 0.47 or 0.48. So 4.7 minus 0.48 gives you the answer over here. 4.2 something you'll get probably. Did you understand this? Niranjan, did you do the same thing? Okay. Now, the third portion of this question is what? When we add question C, we add 0.150 ml of 0.1 mole of NaOH. 50 ml of 0.1 mole of NaOH. What is the millimole of this? Again, it is 5 millimoles. Right? Again, it is 5 millimoles. Now, in this, again, you see the equilibrium exists between these two reactions, which is the acid CS3COOH. It dissociates like CS3COO minus and H plus, and another one that is salt CS3COONA, CS3COO minus plus Na plus. Okay. Now in this solution, we are adding NaOH. Sorry, we are adding NaOH into it here. Okay, NaOH we are adding. So NaOH actually combines with this OH minus that you are giving, because this is base we are adding. So we are giving OH minus into this. So mainly dissociation of this only. This is weakly ionized. Dissociation of this will be very less because of again common ion effect. Here you see common ion effect. So the concentration of Na plus will be far more than that of H plus. So this OH minus combines with Na plus over here, right? And forms what? Na plus plus OH minus, and it gives NaOH in the reaction vessel, right? So obviously when this is combining with this, so this reaction is going, when you add base into it, the second reaction is going into forward direction. When you add acid into it, the first reaction is going into backward direction. That is how it neutralizes the additional OH minus or H plus that we are giving in, right? So this is the extra OH minus we are giving in. It has to neutralize to maintain the pH since it is a buffer solution, right? And it is neutralized by this NaOH, Na plus and OH minus. Now when this reaction goes into forward direction, obviously the concentration of CS3COO minus in the solution will increase. And how it increases? 5 millimoles of this combines 5 millimoles of this, so extra 5 millimoles of this CH3CO minus forms. So that will be again 10 plus 5 here, 15 millimoles of CH3CO minus will get. And what about acid? Right? Acid concentration will decrease, right? So that CH3COOH will then forms 10 minus 5 is equals to 5 millimoles here. So salt concentration is increasing, acid concentration is decreasing. So pH of the solution, that will be pKa plus log of salt by acid. Salt is 15, acid is 5. So 4.7 plus log 3, that will be your answer here. 4.7 plus 0.47 or 48, whatever you take, that is the answer we'll get here. Understood? Okay, so you're trying to think on this question again at home. Okay, this is a very good question which actually helps you in to understand the question how buffer solution works. Okay, but again, if we take the class, we'll take the revision class of this. We'll discuss this again the working a buffer solution. Okay. Now there are some facts that you must keep in mind, that for effective buffer, the ratio of salt by acid should be in this. This one you write down, salt by acid should lie in this range for effective buffer solution. Okay. And with this, if you put, you'll get the range of pKa. You can find out this with the formula pKa minus 1 less than equal to pH pKa plus 1. This question they have asked many times in the exam. For effective buffer, the pH range should be this. You can put this and this value into pH formula, you'll get this. Right. One more thing here, you see the log of salt by acid concentration that you have, or in case of basic buffer, salt by base. Okay. This particular portion, this log part in the formula, this gives you the change in pH, delta pH. So if they ask you what is the change in pH, you have to find out. Effective buffer solution means what, Niranjan? That see, we must have the ratio of the salt of concentration and acid for a solution to behave as a buffer solution. Like all other solutions are not buffer solution. For that, we should have a definite range of salt and acid, concentration of salt and acid, right? So that ratio we must have. So for effective buffer solution means for a solution to behave as a buffer solution, the salt by acid ratio is found to be in this range. Minimum is 0.1 and maximum is 10. Okay. So this point, this term, sometimes they ask this question also. And when you put this ratio 0.1 and 10 into this particular formula, you'll get the range of pH. On the basis of this, we'll get this pH. This is actually the experimental value we have. Okay, 0.1 to 10. That's the thing, right? So, but this thing you keep in mind. Sometimes they ask you this thing directly. And how do we get this formula we have here, right? Salt by acid is nothing but this portion. First you put 0.1 here, and then you put 10 here. You'll get pKa minus 1 and then pKa plus 1, the pH value. Understood? Okay. Now chalo, we'll see some concepts of general organic chemistry, and we'll try to understand the concept with help of the questions. Okay, questions itself we'll see. Okay. Okay, we'll see now GOC. See, in GOC, like again, we cannot discuss all other things. So we'll directly discuss the various electronic effects, okay, in organic chemistry. That is various electronic effects. The various electronic effects are, first one we have inductive effect. The first effect is inductive effect. Second one is uh, mesomeric effect. mesomeric effect. In this also we'll discuss one concept of resonance also. Hyperconjugation. Just a second. Okay. So hyperconjugation and electromeric effect. Electromeric effect. So first question that they ask from this, that the first three effect that we see that I have written here, these are the permanent effect. Okay, this is permanent effect and this is temporary effect. Permanent and temporary effect. Okay, so what do you understand by this electronic effect? Suppose if I take one molecule like C C C C and X halogen, right? Electronic effect is nothing but the displacement of electrons. Displacement of electrons. How electron, like, displaced from one point to other point. Okay, that's the meaning we have here, electronic effects. Okay, now like I take this example. Okay, obviously this halogen atom attached with this carbon, right, that is more electronegative than the other, than the carbon atom that is present. Okay, halogen atom present over here, it is more electronegative. So what happens, the bond pair that you have here, it is slightly shifted towards this halogen atom, and then it becomes del negative. It will have slightly negative charge, and this carbon will have slightly positive charge. Now when this is positive charge we have, so this will also drag this electron pair to this side. This becomes del 2 plus positive charge onto this, and like this positive charge is what is keep on decreasing as we go away from this X, right? Here we'll have maximum density of positive charge, here we have lesser, here we have even lesser, and like this the positive charge density decreases. And now when this positive charge density decreases, the tendency to withdraw electron or attract this bond pair of electron towards its side is less, right? And we say that this kind of effect, we call it as I effect, inductive effect. Inductive effect. And why it is permanent? Because the molecule is halide only, right? It is alkyl halide, and it is a molecule. Whenever this X is attached with this carbon, this thing we can observe easily, right? That's why it is a permanent effect. Now the 2 3 points that you have here, you have to keep in mind that it involves only sigma electron. It involves only sigma electron, right? Now, and it is what, it is distance dependent also. Distance dependent. And it is found to be, the effect of this is found to be negligible after second or third carbon, mainly third carbon or second carbon also sometimes we say. So after second or third carbon, the positive charge density is almost zero, and then we don't observe any kind of displacement in the electron, right? So only sigma electrons are involved. It is distance dependent also. These things has been asked in the exam also, right? Which of these are distance dependent effect like this, they have asked the question. Okay, so again you have to understand this and keep this in mind. An important point it is. But this thing is not true when we have resonance. Okay, resonance we have, or inductive, or this mesomeric effect. In mesomeric effect, this is not true because there is pi electrons involved, right? There is pi electrons involved, and that is not distance dependent also. For that, conjugation is required. Okay, if conjugation is not there, then no displacement of electron in mesomeric effect. Okay, so there are two three characteristics of this inductive effect we have. This is first thing, permanent effect. I have written over here. Sigma electrons involves. Okay, transmission and distance dependent effect, transmitted along transmitted along carbon chain, right? And it is represented by this arrow. Means the electron is displacing from this side to this side. Okay, so if you see this, 1, 2, 3, 4, and 5, if I write. So this is chlorine, right? So chlorine will drag electron towards this side. This also drag electron. This also drag electron, and like this it goes, right? So it is del plus, delta 1 plus, delta 2 plus, like this. So positive charge density continuously decreases here, right? So this is the characteristics of sigma, or what we say, I effect. Now this I effect, like I said, this is the group that can withdraw electron from the carbon chain. Halide ions are the group, or the halogen atoms are the group which can withdraw electron from the carbon chain, right? So this kind of group with withdraw electron from the carbon chain, we call it as minus I effect. So basically I effect classified into two categories, right? One is plus I and other one is minus I. Minus I group are those group which can withdraw electron or drag electron, withdraw electrons. Plus I are those group with releases electron, releases electron. So in this thing, first of all, you have to keep this in mind, that which molecules are, or which atoms shows plus I nature, or which atom shows minus I nature. Okay, that you have to keep in mind. Since you see, minus I groups are the group which withdraw electron, correct? So they must be electron deficient or positive charge species, right? So some examples I'll write down here that you copy down, and you have to keep this in mind. Examples of plus I and minus I, right? So first of all, you see examples of minus I, minus I group. Maximum minus I is for this NF3 plus. Then we have NR3 plus, NH3 plus, NO2, C triple bond N, SO3H, COOH, minus fluorine, then chlorine, then bromine, iodine, right? COOR, OR, OH. Then we have alkyne, phenyl, alkene, H, right? These are the few examples we have. Actually, we also take the reference of carbon and hydrogen, right? All those groups which has more tendency to withdraw electron than the carbon and hydrogen bond, those are said to be minus I. All those groups which has more tendency to release electron than the carbon and hydrogen bond are said to be plus I. Okay. See, this is the order that is given in any other book, actually. Okay. But if you can memorize this, it is fine. Okay. But I will also suggest to you to, to use some logic, common sense, so that you can compare which one will have more plus I or minus I, because these groups eventually affects the acidity and basicity nature of any compound, right? And that is what the application part we have that we'll see. Okay, so first of all, you should know which minus I group is dominates over which minus I group. Then also, then only you can say, okay, this is more acidic or less acidic. Okay, so few common sense or few logic you can apply to understand. Okay, first of all, if electronegativity is more, as electronegativity increases, tendency to withdraw electron increases, minus I effect increases. We can say this, as electronegativity increases, minus I nature will be more. For example, you see the first one, if I compare fluorine, then chlorine, then bromine, and then iodine, right? Obviously, fluorine has maximum electronegativity, order of minus I should be this. Correct, and that is what the order given here also. Okay, second one, you see, if I ask you to compare the electronegativity of OH and SH, which one will be more? If I ask you to compare the electronegativity of NH2 and pH2, NH2 and pH2. Fourth one, suppose if I give you NH3 plus and NH2, OH2 plus and OH. Tell me, OH and SH, which one will have more minus I? Okay, so first one, the order should be this, because oxygen is more electronegative than sulfur. The second one order is this, nitrogen is more electronegative than phosphorus. Nitrogen is more electronegative than, okay, we have nitrogen only over here, but this is the positive charge. So it has more tendency to withdraw electron, more uh, minus I. Oxygen positive charge, more minus I. Fluorine, oxygen and nitrogen. Fluorine is most electronegative. The order should be this. Right? If we compare this one, CF3, CCl3, CBr3, and Ci3. The order of electronegativity should be minus I should be this. This is the order. Okay. So like this, you can actually compare the minus I nature of the group. Okay. So you don't have to memorize this. Okay. If you keep this in mind, you can do many other questions. Okay. We'll see the application of this also. But we'll see few examples of plus I. Okay. Plus I group, you see. Plus I group. Plus I group means what? Electron releasing. Electron releasing means what? Uh, it must have electron present. So either it has lone pair or negative charge on it. Okay, that is the logic you can keep in mind. Suppose I have the first one, which is CH2, lone pair, negative charge. It is maximum. Then we have NH, two lone pair, negative charge. Oxygen, lone pair, negative charge. C, I'll write down next then. Okay, all alkyl groups are electron releasing, right? So if I compare this CH3, then CH3, H, H, CH3, H, CH3, and the last one we have CH3 whole thrice C. What is the order of plus I? For this, the plus I will be maximum for plus I will be maximum for this group because it contains three methyl group. You see, if you compare these two, this has electron releasing tendency, this has also electron releasing tendency, this has electron releasing tendency, right? So here we have two electron releasing groups. Similarly, here we have three electron releasing. So maximum for this, then we have this one, then we have this, and the last we have this one. Yeah, so this is correct, right? One more thing you see, for if you have isotopes, right? Suppose we have CT3, tritium, and then deuterium, right? So CT3 will have maximum, then we have CD3, and then we have CS3. This is also important, okay? For isotopes, you must keep in mind. Bond length, if they ask you, bond length of carbon hydrogen bond is more than the carbon deuterium bond and is more than the carbon tritium bond. Sorry, carbon tritium bond, right? So at bond length increases, tendency to lose electron decreases. Okay, that's the thing. Okay, now few examples that we have already seen. Now we directly move to this, some application part of it. Okay, so I effect also helps in determining the stability of intermediates like carbocation, carbanion, and then the acidic basic properties. Okay, so we'll see first the stability of intermediate. First type of question we'll see, and then we'll see the acidic and basic nature. Okay, so from 11th class, who all are there? Niranjan, you there? Okay, Niranjan, Devdas. Sushant is there? No, I don't think so. Anyways, chalo. So we'll see this. Okay, a few examples I'm giving you. Okay, so GOC is the best way to understand GOC is to solve questions. Okay, there is theory that I have told you already. Okay, more application part you will see, more you will understand. Okay, so first one you see, suppose if I take this example. Here we have positive sign, carbocation, and One more thing is this positive charge. This is fluorine and this is also fluorine. First question is this. We have to find out the stability of this carbocation. Positive charge carbon means carbocation. Find out the stability of this. Oxygen, right? Positive charge here. Here we have positive charge. This is methyl. These two are methyl group. Oh, sorry. Here we have CH2 positive, and then we have NF3 positive, and here we have CH2 positive. Here we have CH3. These two. Okay, the first one. See, all like one thing you try to understand in organic chemistry, if you have any charge species, right? So charge species is always less stable, less stable than the neutral one. Okay, always less stable than the neutral one. Okay, so if you have any charge species, if you are able to neutralize the charge, then the stability you are gaining, right? So all these charge species you see, right? If it is neutralizing by these groups, right? And that is only possible when it releases electron, right? So what we can write down, stability of carbocation, stability of carbocation is directly proportional to plus I group and inversely proportional to minus I group. Okay, that we can write. Minus I means what? It withdraws electron, right? When suppose we have any positive charge, right? And when it withdraws electron, then positive charge density will increase, right? Suppose if I take this example, one example I'll take here, that is CH CH2 positive, and here we have fluorine, right? Another one we have CH2 positive, and here we have OCH3. Just a second. Hello? Sorry? It's done. Done. Okay, right. So these two examples I am taking, right? And one more example, suppose if I write this. Okay, this one you let it, we will discuss later. CH2 positive and CH3. This is the three examples I am taking. Okay. So stability of carbocation, you see, both are positives. First of all, you compare these two. It will be easy for you to understand. Okay, especially for those 11th class students. Okay, so you see this F has minus I nature, right? So it withdraws electron, and when it withdraws electron, the positive charge density on this carbon increases, right? This CS3 has tendency to lose electron, so it releases electron. So electron is going onto this carbon, so positive charge density here decreases, right? So whenever we have increase in positive dense charge, the stability will be less because we have to neutralize the charge species, then only the stability will be more. So if positive charge is there, then electron you have to push to gain more stability. If negative charge is there, then electron you have to withdraw, right? And that's why we are saying carbocation means positive charge carbon, directly proportional to plus I and inversely proportional to minus I. If you take this one, right, this one and this one, if you compare, this oxygen has tendency to withdraw electron, right? So that will increase the positive charge density here. But this tendency is less than this, right? So stability of this is more than this CH2F here. So if you compare the stability of all these, this is the first maximum stable, then the second is this, and third is this stability of this. Okay. Now with this logic, we'll try to solve these examples that I have given you. Okay. So now you see the first one. The first one, these are methyl electron releasing group, right? Electron releasing. And these are fluorine, so electron withdrawing group. So electron withdrawing, positive density here increases, so stability will be less, order will be this. Here you see oxygen has electron withdrawing nature, and this methyl has electron releasing nature, right? So stability of this will be more because the positive charge will more neutralize here. CS3 electron releasing nature, NF3 electron withdrawing nature. Stability of first is more than second. This is 3-degree carbocation, this is 2-degree carbocation, and this is 1-degree carbocation. 3-degree carbocation is most stable, then 2-degree, then 1-degree. Why? Because it has 3 alkyl group to release electron. It has only 2 alkyl group, and this has only 1 alkyl group. So this is the order of I effect that we have. Order of stability of carbocation according to I effect. OCS3 is more stable than F. What happened, Pratik? See, OCS3 and F minus I nature, if you see, first of all, the order that I've given you in that you see, F has more minus I nature than OCS3, right? And if you know the order, it's fine. Otherwise, you can logically, you can understand this. Fluorine is withdrawing electron. Oxygen is also withdrawing electron, but this methyl has tendency to release electron, right? Because of this electron releasing tendency, the tendency to withdraw electron of oxygen will decrease here. First case. Second case, anyways, if you compare fluorine and oxygen, fluorine is more electronegative, so that will withdraw more electron. Oh yeah, correct, Pratik. Then yeah, right, right. So these are the few examples of stability of intermediate, right? Like carbocation and all. Fine. Now in this, if you see the stability of or the acidic and basic nature, right? Acidic strength and basic strength we see. Oh, some more examples we'll see into this for carbanion. Okay, just reverse of this carbanion, and then we'll see acidic and basic strength here. We can extend this class up to 12:15, right? Do you have any other class after this? Can we extend this class up to 12:15? Okay, okay. Chalo, we'll take this class then till 12:15. Okay. You see this, tell me the stability order of all these. First one, negative charge, negative charge, and negative charge. First one is this. Second one is this. Chlorine. Chlorine negative charge we have here. CH3, CD3, and CT3. Isotopes of hydrogen. Tell me the answer in all this. Yes. Okay. The first one, the first one you see, it is the carbanion, right? Negative charge we have. So in this, what we can apply the logic that stability of carbanion, just reverse of that carbocation, carbanion is directly proportional to minus I group and inversely proportional to plus I group, right? Directly proportional to minus I, inversely proportional to plus I, right? So here you see this is 3-degree carbanion, this is 2-degree carbanion, and this is 1-degree carbanion. It has 3 electron releasing group. So stability of this will be least, then we have second, and then we have first. Right? In these two, you see, in this, the chlorine is closer to the compound that you have over here, and this chlorine has minus I nature. So the electron density here will increase more than here. So obviously the stability of second one is more than to that of first one. Oh, sorry, it is in the reverse order, no? This is withdrawing, correct. The stability will be this. Okay, first is more than second. Now you see NO2 and NF3 both has minus I nature. NO2 and NF3 both has minus I nature. But since we have oxygen here and we have fluorine here, so which one will have more minus I? Fluorine, right? So minus I of NF3 is more than to minus I of NO2, and one positive charge also we have here. This will withdraw more electron. So obviously the stability of second is more than to that of first, right? CH3, CD3, CT3. This has maximum plus I, right? CH3 shows plus I effect, no? So both, all these three will show plus I. But plus I of CT3 is maximum, I told you this. Plus I is electron releasing. Electron releasing. So stability is minimum for this, maximum for CS3, order will be this. Correct? Okay. Now next, the last thing that we'll discuss today, that is acid base strength. Acid base strength. Okay. So in organic chemistry, we'll consider the acidic strength. It is CD3 Ritvik, not CO3. I said it is CD3. So shouldn't the last one be opposite? Okay, let me check. Last one, you see, what is the question? That is isotopes of hydrogen, right? You see, CH3 has plus I nature, and the plus I nature of for CT3 is maximum. Understood, Shweta? Plus I nature of CT3, see the plus I nature of CT3 is maximum, right? CT3 has maximum tendency to lose electron. Tendency to lose electrons, right? This is CD3. I told you this. CT3, the plus I nature of CT3 is more than to the plus I nature of CD3 and that of CH3. So mode will be the plus I, mode will be the electron density here, and less will be the stability. You see, stability is inversely proportional to the plus I effect. That's why the third one is the least stable. Yeah, because there is negative charge on the top, and plus I nature will decrease the stability. Okay, okay. Now you see the acid base strength. You see, in organic chemistry, like I said, the acidic strength we define by the tendency to lose H plus ion. However, we have two, three more, definitions of acid tendency to, in with respect to the lone pair and all. But in organic chemistry, acids are those compound which loses H plus ion. H plus ion in water, H2 with respect to water. right? Generally we take with respect to water. Okay, and any compound, right? Suppose RH or any other compound, right? Any compound, if it loses H plus ion, the ion that we get after losing H plus, that we call it as the conjugate base. Okay, and the strength of an acid depends upon depends upon the stability of conjugate base, right? Stability of conjugate base. So suppose if I take this RCOOH, uh, RCOH, okay, or suppose if I take this here CH3COH, okay, CH3COH, and suppose we have C2H5 COOH. Now, this is the acid, and we have to compare the acid strength of this. So, what we'll do, we'll just form the conjugate base of this minus H plus. So, when it loses H plus, what it forms CH3 COO minus. And when this loses H plus, it forms minus H plus, it forms C2H5 C double bond O and O minus. Correct. Now, this is the conjugate base of this acid. This is the conjugate base of this acid. Any acid you have, right? Suppose we have H2O. When it loses H plus, it forms what? OH minus and H plus. So OH minus is the conjugate base of H2O. If you have HCl, so its conjugate base is Cl minus. We have HSO4 minus. Its conjugate base is SO4 2 minus. Just you release or just you remove H plus from that compound. Okay. And now when this conjugate base is more stable, it means for this molecule, the tendency to lose H plus ion will be more, because on losing H plus ion, it is forming more stable conjugate base. Correct? That is true for this compound also. So if the conjugate base is more stable, the tendency to lose H plus ion will be more, and hence the acidity will be more. Okay, CH3CO. I'm coming back to this, Pratik. So you see, if you check the stability of these two conjugate base, okay, so that again depends upon the plus I nature of what? Plus I nature of CS3 and C2H5. So this is the both shows what? Both shows plus I effect. This is also plus I, and this is also plus I. And because of plus I, we know the stability of anion decreases. These are the negative charge anion. So because of plus I, the stability decreases. But which one will show more plus I? C2H5. Larger group, C2H5 shows more plus I effect. So that's why the stability of this compound is lesser than to this compound, and hence the acidic order is this. CH3COH is more stable than C2H5. So one more thing you can write here, acidic strength is directly proportional to minus I effect and inversely proportional to plus I effect. That is the same order of anion strength we have. Yeah, it's relative. It's relative, Pratik. This acidic and basic thing is obviously it is relative. Right? Basic thing, if you have to compare, because you compare acidity and then reverse of that will be the basic order. Okay, that is a simple thing. Few examples we'll see, then probably you'll understand. Yeah, right. C2H5 is even more weaker. Okay, that's why it is. So yeah, there's this acid and base thing everywhere. It is relative only, right? You see, if you take H2SO4, right? If you take H2SO4, water generally we don't see the what acidic nature of water, H2O, right? We don't see the acidic nature of water. But if you compare NaOH and H2O, obviously H2O is more acidic than NaOH because NaOH is a base. You understand this? So acidic and basic strength is always relative, right? In ionic equilibrium only you have studied HClO4 is the most acidic compound we have. See, if you see a little bit of example, if I'll give you, HClO4 is most the acidic strength of HClO4 is maximum. Okay, and then we have suppose HI, we have HBr, we have right H2SO4 also we have after this, and then we have HCl. Like this, the strength is there. So if you compare HI and HBr, so obviously HI is more acidic than HBr. But if you compare HBr and H2SO4, HBr is more acidic than H2SO4, and then it is true for HCl and H2SO4 also, right? So it is always relative. Okay, few examples you see. One very common type of question that they ask many times, that is HF, HCl, HBr, and HI. Second, ROH, RSH. Fourth, H2S and HCl. RC triple bond CH, RCH double bond CH2, RCH2, CH3. HCN, HCH double bond NH. Tell me. It is acidity order. Acidity order you have to find out. Okay, now you listen to me, all of you. See, one thing for this acidic and basic strength, generally you'll get two types of questions. Okay, in one type, there will be variation in size. Okay, what I said, two types of question you'll get. In first type, there will be variation in size. Variation in size. And what we say that the acidity is directly proportional to the size of anion. Because large size, more uniform distribution will be there of the negative charge, and that's why the stability will be more. Okay, large size, more uniform distribution of negative charge, and stability will be more. Okay, and then in the second type we have the size is not that much varying, but electronegativity is there, right? Electronegativity difference. Size is not that, the difference in size is not that much, but electronegativity difference is there. So in that case, acidity is directly proportional to electronegativity. Now you see these three questions, 1, 2, and 3. In this, there is a variation in size. Fluorine, chlorine, bromine, iodine, oxygen, sulfur, oxygen, and sulfur. Right? There is a variation in size. In this, you see sulfur and chlorine belongs to third period only. There is not much variation. But yes, electronegative difference is there. Right? Here we have carbon and carbon. Electronegativity difference. Here you see this carbon is what? This carbon is sp hybridized. This carbon is sp2 hybridized. And this carbon is sp3 hybridized. Difference in electronegativity. This carbon is what? sp hybridized. And this carbon is sp2 hybridized. Carbon carbon atom size is same, but difference in electronegativity is there. If the conjugate base is stable, Vaishnavi, you think one thing. Yeah. How do you get conjugate base? By removing H plus. So if after removing H plus, if you are gaining stability, it means you will happily lose H plus. No. So that's the thing over here. Conjugate base we get after losing H plus. So if conjugate base is stable, it means the tendency to lose H plus ion will be more. And that's why it is a stable, more acidic compound it is. More stable conjugate base, more will be the acidity of that compound. This is the one thumb rule you should keep in mind. Understood? Another thing you see, like I said, variation in size and electronegativity, these two factors you have to keep in mind. Then you can put some logic. Why the size of anion is directly proportional to this acidity? Because more will be the size. Since the size is this negative charge, and the size is this negative charge. Okay, more will be the size. More will be the distribution, uniform distribution of this negative charge over this anion, and that's why the stability will be more. More uniform distribution means what? More stability, right? So now you see here HF, HCl, HBr, HI. What is the conjugate base of HF? F minus, Cl minus. This is Br minus, and this is I minus. So which has the maximum size? Obviously, iodine has the maximum size, right? So obviously, the stability of iodine is maximum over here, right? So that's why the order of acidity is this. Is it clear? One more thing you can think over here. The bond between this HF is what? It is 1s and 2p bond. 1s 2p. This is 1s 3p. 1s 4p and 1s 5p. Okay, bond length is maximum over here. As bond length increases, strength decreases, right? And bond strength when decreases, tendency to lose H plus will be more. That is also one of the way that you can think. Hi is most stable. Oxygen and sulfur, you see, if you lose H plus, you'll get O minus and S minus. So since S minus sulfur, size of sulfur is more than to that of oxygen, that's why the stability of conjugate base for this compound will be more and acidity of this is more. Yeah, Pratik, like that also you can think. Oxygen being more electronegative draws more electrons, and then the electron density on oxygen is more, that will destabilize that ion. See, whenever we have the contradiction in size and charge, we always give preference to charge. That we always keep in mind. Yeah, more negative charge. See, whether it is more negative charge or positive charge, whenever the charge is more, it is always less stable. Neutral species is always more stable than the charged species. So whenever you have tendency to decrease the charge, you are going towards more stable state, right? If we have contradiction in size and electronegativity or charge, we always prefer charge as the major part here, right? Charge will always have the major factor. Okay, so now you see the first three that I have given you, it is based on the size factor. Oxygen, sulfur, both will have negative charge in its conjugate base, but sulfur having more size, that's why the stability of this compound is more, and hence the acidity of this is more. Oxygen, sulfur, again you see, both will have negative charge in its conjugate base. Sulfur having more size, stability of this is more, and hence acidity order is this. What is the confusion? Tell me. See, listen to me one thing. Just one thing, you listen to me. There are two types of question. One is when there is difference in size, like the first three I have given you, and other one, then there is difference in electronegativity. No, no, no. Wait, listen to me. One is size difference and electronegativity difference. So you don't consider this size and electronegativity. See, I am again explaining this. Okay, you just listen to me. Don't think anything else. I'll explain everything when you have both factors and what you have to keep in mind. Just you listen to me first. First of all, two types of questions are possible: variation in size, variation in electronegativity. Correct? When size variation is there, right? So as the size of an ion increases, acidity increases. This is the thing. I have written it over here. You see, acidity is directly proportional to the size of an ion. This thing. Why it is directly proportional? Because more will be the size, more uniform distribution of the charge will be there, and hence the stability will be there. So when you form the conjugate base of these compounds, as the size of an ion increases, distribution of charge will be more uniform. That leads towards the stability or to that the conjugate base. Wait. Let me explain. Correct. So now coming back to this size factor. First example you understood. F minus, Cl minus, Br minus, I minus. I minus maximum size. So most stable conjugate base, and that's why the acidity order is this. Coming back to the second one. You'll get O minus here and S minus here. Right? So both will have negative charge. Size of sulfur is more. So this negative charge here is more stable. So acidity of this compound is more. And same logic we have applied here. Right. Now, if you have Now, if you have any contradiction, in size and charge, then we always prefer the charge factor into this. Size will not be the major factor, right? So for SH, if you consider size or electronegativity, SH is no, you see, Pratik, like we cannot, here you see, here if you compare these two compounds, oxygen and sulfur, right? So we have difference in size. We have oxygen present here. See, I know where you have got confused. You must have thinking, sir, why don't we take electronegativity of this oxygen and electronegativity of the sulfur, right? That will not take. When we take electronegativity here, you see this kind of compound, you see sulfur and chlorine both belongs to the third period, right? After sulfur we have chlorine, right? So obviously there is not much size difference here, but electronegativity difference is there. If you see, we'll also have the size difference here. So this you have to think, right? Second example, you see this carbon and this carbon, do we have electronegativity difference here? Yes, we have. But do we have size difference? No. So we'll take electronegativity here. But here what we have, when the elements belongs to different group, or sorry, different period, right? This is for second period, oxygen, and this is for third period, sulfur. So when there is different period we have, then we'll take the size factor. Here you see it is clearly understood that size is same. We'll take the electronegativity factor. Carbon and carbon size is same. We'll take the electronegativity factor, right? Sulfur and chlorine size is very much same, right? Very close, but electronegativity difference is there, right? In all these example, you see I have given the term which belongs to the different period. When we have different period, you consider size in that case. Fluorine, chlorine, bromine, iodine, different period. Did you understand? Yeah, it may be. Yeah, Pratik, correct. It may be in some examples. It may be that it won't make any difference. But actual thing is this only. If you have any contradiction in size, and suppose in one example, I have given the variation in size also and variation is electronegativity also. I've given you three, four examples, three, four molecules like that. In that case, we'll go with charge factor, not the size factor. Okay. So the point here is what? All these things according to the size I have given you. This thing, the stability of what? Suppose this forms what? Cl minus conjugate base and S2 minus conjugate base, right? So chlorine is more electronegative. So negative charge on more electronegative is always more stable. So obviously the HCl is more acidic than H2S. Which is more electronegative here? Sp hybridization is more electronegative. So obviously this is most acidic than the second one and then the third one. In these two, again Sp, this is more electronegative. Is it clear now? Tell me. Okay, so Salo, it's 12:30 now. Okay, I'm getting late. Okay, we'll continue with some more example in the next revision classes. Okay. Fourth one, which is the fourth one? H2S and HCl. Okay, H2S and HCl, you see, chlorine is more electronegative, obviously, right? And we have to consider the electronegativity factor. So acidity, you see, acidity is directly proportional to the electronegativity. Here you see acidity directly proportional to the electronegativity. Why? Negative charge, you always keep in one thing in mind. Negative charge on mode electronegative element. Negative charge on mode electronegative element is always more stable. Is always more stable. Reverse of this is also true. Positive charge on mode electropositive element is always more stable. Yeah, chlorine is more electronegative than sulfur. That's why. Okay. So negative charge on more electronegative, positive charge on more electropositive elements are always more stable. Okay. These two things you should keep in mind. Okay. Is it clear now? Yeah. If you take here H2O also, if you take here H2O, right, then this is the most acidic. That's why you see it is again you see it is a relative thing. Yeah, yeah. Right, Pratik, correct. I know where you got confused. Again, you are mixing these questions. Question number 2 and question number 4, right, Pratik? Question number 2 and question number 4 you are mixing, right? Okay, chalo Pratik, we'll discuss this next class, okay? I know Pratik where you got confused, but I'll tell you. See, actually, depending on the question, you have to think that what logic you should apply. It is a bit confusing, I can understand, okay? But then again, I'll discuss this next class, okay? You have another class at 1 o'clock, so I won't take much time, okay? Yeah. We'll discuss this next class. Okay, Pratik. I understood where you got confused, but that is also I have explained. But again, I'll explain again. Okay, don't worry. Okay, chalo. Bye bye. Take care. Okay, we'll discuss uh, some more examples in the next revision classes. Okay. Chalo. Bye bye. Take care. Thank you.